All right, so previous class we were discussing about Henon map, isn't it? Yes, previous class we were discussing about Henon map, but unfortunately some recording issue was there. So my voice is there, but my lectures are not there, like the slides are not coming. So I'll just give you a brief on what we discussed last time. Okay. So here we begin. So yes. So Henon map. Okay, what is Henon map, Miss? So anyway, Henon map is a two-dimensional map. As you see, stuff of the lecture, like we saw this 1D map, the simplest logistic map, isn't it? So yes, and this simplest 1D logistic map shows chaos. Hmm? Then, like, researchers have already learned about this 3D flow. This is the second point. Researchers already learned about 3D flow. This was my second slide of this course. So Edward Lawrence, he found that weather systems are completely unpredictable. Okay, during 1970s, he used like some different initial conditions and he found a flaw. Okay, like the outputs, the results are going haywire. So therefore, he found what is the reason, and then ultimately chaos was discovered. So then he did that for the 3D flow. Okay, the 3D flow, which looks like this butterfly kind of attractor, which you already. Butterfly kind of attractor was only possible due to the stretching and folding action. Okay, so there is some stretching and folding action in this, and therefore this chaos can occur. Okay. Now, researchers, like other researchers, thought that why we need to go to a higher dimensional system like 3D. Okay, cannot we observe this in lower dimensional system? Of stretching and folding? Therefore, Michel Henon, he is another scientist. He thought, can I mimic those properties? Can I mimic those properties in a two-dimensional map? Like that, he discovered this 2D map known as Henon map. So, how we discovered this Henon map last class? Like you took a sheet, and the boundaries of the sheets are of different colors. Okay, and what we did is we transformed the sheet into this a parabolic looking sheet. Okay, how you do that? Stretch it once and then plug the middle point up. So like that you got this sheet. Okay, so this is how to get to that state. You need to apply this map. Okay, you need to apply this map. Then what happens? Then this is a fat sheet. This is a fat sheet. So what you do? You try to make it slim. Okay. So this is the thinner sheet. Okay. Fine. So we only contract these x directions. So therefore you can see only the changes is in the x direction. The y is the same. Y double prime equals to y prime. What happens after that? Just rotate it. Just rotate it. So this guy, if you rotate it, you get this. So this is what is known as the Henon attractor. This is a chaotic attractor and it is Henon attractor. So the composition of this map, T prime, T double prime and T triple prime is what gives us this final output. So going from this to this is the action of the Henon map. Okay. Converting a sheet, converting a two-dimensional sheet into the Henon attractor is what brings us the Henon map. Okay. So you have to compose T prime, T double prime, and T triple prime. Okay, here I have composed, and that's how you get this two-dimensional Henon map. Okay. So as you can see, the two-dimensional Henon map has how many parameters? A and B are the parameters of the system. So you can vary A and B parameters in real numbers. Okay, and you will see the behavior of the dynamics changes. It can be periodic, it can be chaotic, it can be fixed points. Okay. Fine. So this is the action. This is the action. Just a geometric action I want to display to you. So take this round neighborhood. Take this round neighborhood N. Okay. And if you apply the map F, if you apply the map F in the first, it gives you F of N. Okay. So the idea is if you apply a continuous function to a continuous curve, the result will be a continuous curve. If you apply a function to a sheet, to a region, the output will be another region. Okay, not the same, might not be the same region, but it will be some other region. So therefore, if you are starting with N and you are applying the map F to N, then that will be another region. The question is, will it be lying inside the N or outside N. Okay. So if it is lying inside N, then that is something known as like, yes, it is mapping inside. It is mapping inside. So it is a contractive mapping. Contractive mapping. So you can say this. This is something known as a contractive mapping. Fine. In this case, you have N, but when you apply the F map to the region N, it is moving outside. So this is expanding. So this is something known as an expanding map. Okay, so the nature of F is contracting here. The nature of F is expanding. Similarly, here also you can see it is more or less contracting. It is expanding in one direction, the third case, but it is also contracting, right? Therefore, there is a like noodle kind of thing. Okay. So yeah. So this is sometimes you can see like this is like a saddle action. Saddle, neither contracting nor expanding. Okay. So then I showed you some figures like from the paper by Henon in 1976. Okay. So he found that when you take this ellipse structure here, okay, and you apply the map T prime, then you got this structure which I showed. Then then this is fat, so you make it more skinny. Then you rotate it. Then you rotate it, and that's how you get the Henon. Okay, Henon attractor. And what is the speciality about this Henon attractor here? The Henon attractor is chaotic, and at the same time, it is a fractal attractor. Like it is having a fractal structure to it. Why it has fractal structure to it? You can see this figure. This is the Henon attractor which you have plotted in Python using Python. Okay. And yes, so what he did, this is from the paper of Henon also. This is the paper by Henon in 1976. So it is very nice that in 1976 he can draw these pictures. And you can see the axis labels also. So it reminds you of old times. Okay. So nowadays the axis labels are very pretty. So what you can do is you can take the zoom of this region A, okay, and this is shown on this side. You can see. Now take the zoom of that another small region, and yes, where it is, yeah, you can see the structure here. Take again the, you again see some structure here. So, okay, so it is never-ending structure, self-similar structure. So therefore, the Henon map has a fractal microstructure to it. You can compute the fractal dimension of this attractor. I would suggest maybe Google yourself. Google yourself, how can you compute the fractal dimension of the Henon attractor? Can you guess what should be the dimension? See, it is looking like a curve, right? The Henon attractor looks like a curve. Yes, but it is lying on a 2D plane. So the fractal dimension cannot be less than 1. It cannot be greater than 2. It has to lie in between 1 and 2. So that's how you can make a bound of that fractal dimension, logically thinking. Okay. So the fractal dimension of the Henon map will lie in between 1 and 2. But what is the exact value? You have to apply the methods I have taught in the class. Box counting dimension and other dimensions. Okay. Similarity fractal dimensions. Okay. So then we had this exercise in the class. We had this exercise that is Henon took A equal to 1.4 and B equal to 0.3 and he found the chaotic attractor. Okay, so from then onwards in his paper, these are considered to be the standard values. These are considered to be the standard values for the chaotic Henon. And this is exactly, you saw something on your text, isn't it, in Python? All of you were showing me what you did. You started from two different initial conditions for the same set of parameter values. For the same set of parameter values, you started from two different nearby initial conditions and you iterated your map. And exactly, did the blue and red trajectory completely overlap? It did not. So that therefore you can see that for the same parameters, one would expect, a layman would expect that you will get the same set of data because it's the same map, same parameter. But since the chaotic nature, you are getting a totally different output. But when you plot both of them, you will get the same Henon attractor. So why we are getting the different points, can you know? Can you understand? It's because of the sequence of the points. It's due to the sequence of the points. Like maybe it is going here first, here second, but in your other case, it might not go start from that point. It might be here and here. But anyway, it will traverse all in the attractor. But the sequence is different when you start from another initial condition. Therefore, the time series is different. So that's a very nice aspect of the chaotic nature. So this is what you did in the last class. And moreover, you can find a trapping region of Henon map also. What is a trapping region? Trapping region means this is the Henon attractor, okay? And A, B, C, D are the trapping region. Okay, what does it mean? If you start any of your initial condition inside this A, B, C, D parallelogram, it will converge into the attractor, into the chaotic Henon attractor. If you start anywhere outside of this, it will diverge off to infinity. Okay, so you can see, and Henon has proved this parallelogram by himself that this is the trapping region for them. Usually, computing trapping region is a bit difficult task. Okay, you have to it is computationally intensive, but at that time he was not having that much computational power, so he thought, why not I show it by my mathematical skills? And he actually got this. Actually, you can find the equation of each of these lines. That's how effective it is. Fine. Then we discussed, like, if you want to explore on this, if you want to explore more on this, so there is a very nice book by Elhaj and Sprott, Clinton Sprott. Okay. You can download this book. Okay, for World Scientific 2D quadratic and 3D ODE systems. Okay, and in this book, this is a part of the page I have taken. So you can see these are all attractors of 2D maps, and they are like, and all are done computationally using his computer at a very old times. But you can see how beautiful these structures are. How beautiful these structures are. Like, if someone will get amazed by seeing these structures. Okay, like at the same time, these are not random structures. At one point, chaos and random are totally different things. Okay, chaos and random are totally different things. How they are different, I will tell you. For chaos, suppose you take random, I will tell you, take random numbers from this area, from this parallelogram ABCD, 1000 random numbers you plot in this region ABCD. Okay, so what you do, what it will do, it randomly it will plot, right? Randomly it will plot. But it might be that some chunks of the points are biased and they will lie in one region. You can see 1000 points are plotted throughout, but some chunks are here. So this can be a random thing. But if it is a chaotic thing, if it is a chaotic attractor, A, B, C, D, if it is chaotic, then it is very nice. It is very nice. Why it is very nice? Your points spread out throughout the region. It will cover all the region. It won't get biased. Okay? Like, the points can be spread out totally. Okay? You can see now the difference between the random and the chaotic nature. Huh? What if it is not random? Chaotic time series, chaotic data are not random at all. Why I told you that point? You can see randomly, if you're selecting one, if you're plotting 1000 points in the region ABCD, it might get biased, right? It might get biased, and many of the points will be lying in this tiny region. But in chaos, it's not the fact. In chaos, it can easily spread out. Okay, easily spread out. That's how nice it is. Yeah. Had the equation for chaos, the Henon map. Maybe later we can discuss. Huh? Yeah, it is unpredictable. It is unpredictable, and you can see that it has a fractal structure also. What I am saying is, if you take chaos, you can easily distribute points in a region. That's what I'm saying. Anyway, so these are the attractors, very striking looking attractors. Like, at the same time, you can say, like, if you ask a layman, if you ask a layman, you ask a layman to draw this structure, okay? If you ask a layman to draw for this. Okay, so that's how tricky it is. Okay, let me know if someone wants to start a startup. We are thinking actually. We are now thinking like walk around like. Okay, so we were thinking like if we can make some necklaces out of this, like something like good things out of this, and it can be a good startup for this. Hmm? I will show you a more even good one. This one. You see this? These are even nice. Okay, these are even nicer. I have taken it from the website. I showed it last time. Okay, so we are actually thinking of 3D printing this. It is in progress. We are thinking. So yeah, you can find from these websites. I've just taken a snapshot from HoloVis, examples to HoloVis. You can go to this and see like these chaotic attractors are something more than just uh, points. Okay, let's come to something known as a horseshoe map. Okay, I remember that you must have known about horseshoe, isn't it? Has anyone seen the shoe of the horse, like the feet of the horse? Yes, is it like this? Like parabolic kind of. So you can assume that it is like. So the idea is pretty similar for the Henon map. The idea is pretty similar with the Henon map. Okay. Well, what is that idea similar? Okay. Yeah, we need some distance. Yes. So take this sheet here, A, B, C, D, E. Okay, A, B, C, D, E. Okay, and take it. I marked a point very cunningly. I marked a point, and I have given different colors to this A, B, and C, D, and E. Then what I do is I stretch it. I stretch it like this in the parabola. Can you imagine that it is going in your mind like it can happen? The structure can happen. Can you think in your mind? This structure can happen. Everyone? Yes. Now repeat the same process again. Repeat that same process again. How can you repeat that same process again? Take this guy, take this sheet and push it here. Push it here. Okay. So think about it. Okay. Think about it, and you will get some structures like this. Finally, if you do more and more and more, you are getting more and more thinner structure, like noodle-like structure. Okay. They are of increasing length. Okay. Lot of lengths, but they are fitting inside. It can be in the first instance, isn't it? Yeah, you can expect like that, but there will be dimension. There will be dimension. So this is what is known as the smale horseshoe. So the smale horseshoe is known as the hallmark of chaos. With this and analytic clarity, it robustly describes this homoclinic dynamics. Okay, homoclinic dynamics you don't need to know more now. Okay, we can learn it in a later stage. Okay, but you don't need to understand. It's more intricate, which was encountered by Poincaré and studied by these people here. Kirchhoff, Cartwright, Littlewood, and Levinson. So David Ruelle has called Smale's 1967 article. So Smale wrote an article on that and called it a masterpiece of mathematical literature. It is still worth reading today, like hyperbolic dynamics on hyperbolic dynamics in 1960s. You can actually go to this website. I have taken these snapshots from this website. American Mathematical Society has a section, has its own newsletter known as What Is. What is. So here it called What is Horseshoe Map. So try to search what is Horseshoe Map, AMS, and you can get this website there, and many other dynamical literature is there. I have taken this just for the sake of the class. Then there is something known as Baker's 2D map. But yes, let me tell something here more. Isn't it something you do with parota? Isn't it something you do with parota? Isn't it? Take this, make another round, then make another round, make another round, lot of layers. Again, bring it down to the round shape, roll it down. So that's how you get these layers and layers inside a spiral structure. So this is known as kneading. This is known as kneading dynamics. kneading dynamics, and this kneading dynamics is actually the Baker's map was inspired, and this is how chaos is found. Okay, so actually the parota you are eating is actually chaotic. Okay. So this is the Baker's 2D map. Another map, I'm just showing it here just to give you an intuitive idea. Hmm? So don't worry about this map, like it is defined in this way. It might be complicated something, but see this picture here. See this picture here. Okay. This is the picture A. And what you do is flatten and stretch. Okay. You flatten and stretch this. So of course you can get this. Then you cut it and stack it together. Okay. So a more detailed version on this, I would like to play here. Let me see if you can understand this part. So Baker's map, this is a nice website where it shows this actual structure in place. Like you can see what is happening here. Okay. So it reminds me of bubble gum, isn't it? Bubble gum was of this color. Boomer, is it? Boomer. So actually, this is what you do when you need the dough, kind of. So therefore, I thought of giving a class assignment. Like we'll bring like this pot and we'll have some dough, put some food colors different, and roll it. Then we see how different colors are spread across the dough, and it will be very nice and complex. Hmm? So you can see, yeah. So that's how. Hmm? Volume is conserved. Yes, fine. No, no, no. You are seeing this 2D. Why it is 3D? Yes, yes. The idea is like you are taking two squares of different color and you are merging them in such a way that you see this complicated dynamics. But the details of it, like what happens to the area and all, that are a bit detailed things. When you go and work on it, actually you'll get. Hmm? So maybe if you're interested, like you can see how two different colors are so like chaotically distributed in the sheet. Okay. So I believe if we do it in a dough in this class, we will see the exact same structure. Shall we do it as an experiment in the Oh yes. Maybe the last class we can do, isn't it? But we have some good food colors. Like one food color is magenta, I think. Magenta we can get from beetroot. Yes. And uh, green you can get from spinach. Green, magenta, and carrot also, I think. Carrot. Let's not take, let's take carrot or beetroot because two colors are almost similar. Beetroot we can take. Turmeric, yes, yes, yes. Ah. One good way also, someone can bring milk. Okay, milk. Okay. What we can do is, just put that milk, okay, and just put some haldi powder on the top, okay, and just some, what you call that, spinach and beetroot, the color, and mix it together. You will exactly see these kind of chaotic patterns. Okay. So that is actually coming from fluid dynamics. That is actually coming from fluid dynamics because milk is a fluid and you are putting something and mixing. But in fluid dynamics also there is chaos. Chaos can enter anywhere. That's the best part of it. So maybe in the last class we can do this experiment, isn't it? Sounds good, isn't it? And we can record it. Okay. So this is all about our where it went. Yes. So this reminds me of something known as the Russian dolls. Okay. So this is there in Russia. Huh? So these are Russian dolls known as Matryoshka dolls. So what is special about these dolls? Some of my Russian colleagues also told me about this. Okay, so in some our mini project students are working with them. Okay, so they know already. So this doll is like you take this doll, you take this first doll, okay, and inside this big doll, this will be there. Inside that, this will be there. Inside that, this will be there. This will be there. So if you are trying to pluck that doll, inside one doll you will get another. Inside another doll you will get another. It's never ending. So this is the best part of it. Um, hmm? No, size will be decreasing. Hmm. Okay, so there exist these dolls of like bigger shapes. Imagine that if you take a bigger doll, then how you will be bored of taking out a lot of dolls out of it. Anyway, so this is all about 2D maps, and yes, I think I tell one more important thing here. This is taken from my PhD thesis. Okay, so I spent a lot of time drawing this curve. Okay, so I thought of including this. Okay, so if you have a 2D map, if you have a 2D Henon map, suppose 2D map x prime and y prime, say x prime y prime, you can write it in terms of matrices. Maybe a good way is xn plus 1, yn plus 1, write it in terms of matrices is say some f of xn comma yn. Fine with you? This is some g of xn comma y. Understand what is the stability, like how you can find the fixed points of this map. How can we find fixed points of this map? You know about 1D maps, how to compute fixed points. In 1D map, for a 1D map of this kind, xn plus 1 is f of xn, the equilibrium point is given by the solution of this, x star is f of x star. Now for a 2D map, the fixed points, for a 2D map, the fixed points are given by x star comma y star. There are two x's, right? X and y. So there will be x star and y star. Now how can you get x star? X star is f of x star y star, and y star equals to g of x star comma y star. So you have to solve this simultaneous equations. Simultaneous equation. You have to solve this simultaneous equation. All right. You have to solve this simultaneous equation and get the fixed points of the map. All right. Okay. So, but after you get the fixed point of the map, how can you deduce that the fixed point is stable or unstable or saddle? Take the derivative. Yes. In 1D maps, you were able to take the derivative very nicely. Yes, because you had one variable and you just took df by dx. And what you were checking, if mod of the derivative of the map is less than 1, then x star is stable, else unstable, isn't it? Okay. Now, in the case of 2D map, how you will proceed? In case of 2D map, researchers found that it is not that simple. It is not that simple because here you have two variables instead of one. Here you had one variable x. One variable x. So derivative worked. Worked. But here, in this case, yes. So in this case, like you have two variables. So the derivative doesn't work. So there is a generalization of the derivative that works here. Can you tell me what is the generalization of the derivative here in dimensions? What is the generalization of a derivative in 1D? If you want to go to 2D, what kind of derivative you can use? Partial derivatives. Okay, good. But what partial derivative you will use? That is a confusion. Dou f by dou x you can take. Dou f by dou y also you can take. So which one you should take? dg by dou g by dou x also you can take. Dou g by dou y also you can take. Now all of these are important. Therefore, Jacobian created a Jacobian matrix and put all those parts. That is known as Jacobian matrix J, that is df by dx, f by dy, dou g by dou x, dou g by dou, isn't it? That is the Jacobian matrix. That is the Jacobian matrix. Okay. So what you do with this Jacobian matrix? Solve an example actually. Then only you will understand actually. Anyway, so this is the Jacobian matrix. So you in that Jacobian matrix you evaluate it at the fixed point x star and y star. Okay. So there will be numbers. Finally, I am trying to say that the Jacobian matrix will have some numbers. Okay, some numbers here 2 by 2 matrix. Now, researchers came to know that the stability of the fixed points depends on this matrix, okay? And how they can understand, like how can understand this concept like of stability? I think if you remember, I told you about eigenvalues, no? If a fixed point is stable, all eigenvalues should be less than 1 in modulus, isn't it? I told you that. So from this matrix, can you find eigenvalues? Yes, you can. You can find eigenvalues, isn't it? You can find eigenvalues. What do you have to do? Determinant of j minus j star minus lambda equal. From that you can compute the eigenvalues. Yes, and check if there will be two eigenvalues because it's a 2 by 2 matrix. So check if mod of lambda 1 is less than 1 and mod of lambda 2 is less than 1. If it is the case, then x star, y star will be stable. Isn't it? How many of you did not get this? Is it okay? Is it okay or no? Yeah. Okay. So what we did, you take the Jacobian, evaluate it at the fixed point, then find the eigenvalues of that Jacobian, isn't it? If you find the eigenvalues, how many eigenvalues will be there? 2, because it's a 2 by 2 matrix. You should be confident. Why is control of eigenvalues, no? You will get eigenvalues, what you will get? No, mod of lambda is less than 1. That means lambda can be in between -1 and 1. Think what is, think lambda 1 is minus 0. Does it satisfy this condition? Yes. So lambda 1 has to be in between -1 and 1. Lambda 2 has to be in between -1 and 1. Okay. So therefore, x star and y star is stable in this case. Now, if one of the lambda 1 is less than 1 and the other lambda 2 is greater than 1, it is having a mixed nature, right? One is less than 1, one is greater than 1. I told you that mixed nature. Mixed nature means it is yes, it is a saddle fixed point. Okay. Now, other condition is also there. What is the other condition? Both the eigenvalues are greater than 1 in absolute value. Then it is unstable because all are mixed nature and all are greater than 1 in absolute value. Okay, with you? Complex. Therefore, I am telling you the magnitude I am giving. No, the magnitude you have to compute. Yes. So if you do 0.1 I plus 0.1 J or A plus BI, then you take the modulus means root over A square plus B square. Yeah, it takes all the things. It will take the absolute values. Just take the magnitude. That's it. It's clear. Now there is a catch. What is the catch? Computing. Researchers found that computing eigenvalues. Remember, when you compute the eigenvalues here, you will have a square root, isn't it? Will you have a square root while computing eigenvalues? It will be a characteristic polynomial, no? Yes. So when you will solve the quadratic equation, lambdas will be the roots of that quadratic equation, characteristic polynomial. And you will have that root over formula, minus b plus minus root over b square minus 4ac by 2a. Yes. Isn't it? Isn't it? No. Okay. Maybe. We should do an exam. Okay. How about we compute the fixed point of the Henon map? Can we compute the fixed point of the Henon map? Yes. So just see this 1 plus a y minus ax. So this is the 2D Henon map. And you know that it is chaotic map, okay? Can we find the fixed points of the map, x star and y star? So what you have to do, x star should be set to? No, that is for the continuous system, 1D flows. Remember carefully, for one of the flows, the definition of equilibrium point and stability of equilibrium point is totally different from the discrete map, equilibrium point and their stability condition. Don't mix them up. Okay. X star equals to 1 plus y star minus ax star, right? Square. And y star is just bx star, isn't it? Now, can you give me the value of x star and y star from here? What is x star and y star? Tell me the value. Substitute the value like that, Mr. Bhanu suggested, and try to do that. Can you give me how, just from seeing this, can you tell me how many roots you will get? 2 roots. So there will be 2 fixed points. Can you tell me what you got x star and y star? Let us call it x1 star, the fixed point 1. And you already know that there will be 2 fixed points, isn't it? Tell me, what is x1 star and y1 star? Anyone you tell, maybe the plus 1 you tell. Plus. Hmm. E of x1 star. Okay. This is the fixed point. Hmm? And what is x2 star, y2 star? It's just the same, but there will be minus here. So these are the 2 fixed points of the map. Hmm? Now the question is, how can you compute the stability of these 2 fixed points? That is the question. What you will do, compute the Jacobian matrix of the map. Jacobian matrix is equal to, consider this to be F, consider this to be the G. So what is Jacobian? Dou F by dou X, dou F by dou Y, dou G by dou X, dou G by dou Y. Okay. What you get from here? Dou F by dou X is dou F by dou Y. G by dou X. Okay. Now you know that Jacobian doesn't have a Y part. Okay, Jacobian, inside the Jacobian, the entries, you don't have a Y. Okay, you only have the X. Okay, you only have the X. Now, can you tell me, like, what is the eigenvalues in this case? What should be the eigenvalues? Okay, so we will have 2 Jacobian matrix, isn't it? You will. So one Jacobian matrix will be minus 2a x1 star 1 b 0, isn't it? Another Jacobian matrix will be minus 2a x2 star 1 b 0. Fine. 2 Jacobian matrix corresponding to 2 fixed points. Now, can you find the eigenvalues in both of the cases? What should be the eigenvalues in both cases? What we do, our normal procedure is determinant of j minus lambda I equals to 0. So, determinant of minus 2a x1 star minus lambda 1 b minus lambda. Can you solve this? What should be it? So lambda times 2a x1 star plus lambda minus b equals to 0. Lambda square plus 2a x1 star lambda minus b equal to 0. Lambda x1 star plus minus b square. B square means maybe it is good to keep it 2a x1 star because there is a 2a here. I don't want to disturb that. So I'm not squaring it. Okay. I'm not squaring it. I don't want to make it more complicated. x1 star square b square minus 4a1 c is b divided by 2a, that is 2. Okay. Fine. So what are you getting? This is the assignment for the next class. This is the assignment. You got lambda, so you will have two eigenvalues. Put lambda 1 less than 1 and lambda 2 less than 1 to find region of in the AB plane where x1 star, y1 star is stable. Isn't it? You can get this region, no? Put this condition. You will get lambda 1 from here. You will get lambda 2 from here. Put the condition mod lambda 1 less than 1. Nothing else. You will get a condition on A and B. That's what we need. Same you do for this. Same you do for this. Compute again the other lambda 1 and lambda 2. Put mod lambda 1 less than 1. Put mod lambda 2 less than 1. And give the conditions on A and B. Yes. Seems pretty hard, isn't it? Seems pretty hard. Okay, but this is the assignment. This is the assignment. But there is a catch. There is a catch. Why I told you this fact? Can you tell me? Any ideas? So you know why it is getting too difficult. Why it is getting too difficult? Because there is a square root. I wanted you to realize that it is not that easy. So I made you do this calculation. Okay, but you have to do this calculation in the assignment. But there is a other way around. There is another route to this. Okay. So instead of, we know that stability depends on the eigenvalues. Stability depends on the eigenvalues. Mod lambda 1 should be less than 1 and mod lambda 2 should be less than 1. But there is another way out. That's where I showed you this picture right here. Okay. So instead of computing eigenvalues, just compute the trace and determinant of the Jacobian matrix. Okay. Compute just the trace. Just watch my red part. So suppose your Jacobian matrix J is A, B, C, D. Can you tell me what is trace of J? Tau. This is known as trace of J. Trace of J is the sum of eigenvalues. That is lambda 1 plus lambda 2. But it is also related to the elements. That is, it is a sum of A and D, the diagonal element, A plus D. At the same time, determinant of J, we usually call it delta, is the product of eigenvalues. Okay, but it is also related to the matrix element as A times D minus B times. Okay. So you just, instead of computing the eigenvalues, which involves a square root, you compute the trace. Okay. Compute the trace and you compute the determinant of the matrix. So this is what it shows in the diagram. This is what it shows in the diagram. So this trace is the determinant of the Jacobian matrix. This tau is the trace of the Jacobian matrix. Okay, fine. You put the trace on the x-axis, put the determinant on the y-axis. Okay, then you will get this triangle. This triangle, you see, the inverted triangle is there, bounded by three straight lines, isn't it? It is bounded by three straight lines. What are those straight lines? Delta equals to 1 is one straight line. Delta equals to minus tau minus 1 is another straight line. And delta equals to tau minus 1 is another straight line. If your tau and delta value of the fixed point lies inside this gray region, inside this region, okay, which is colored very nicely, then your fixed point is stable. Then your fixed point is stable. Okay, fine. If it is lying anywhere outside, that like if it is lying here, like in the punctured region, idle fixed point. Okay. If it is lying here where nothing is done, it is repelling or unstable. So this is what is usually known as a stability triangle, which was my title of this slide. Stability triangle. Okay. So instead of computing the eigenvalues or these things, you can just find the trace and determinant, okay, and use this. Determinant will also be constant. Delta equal to 1. Tau minus 1. It's a line. Here on that line, tau and delta vary so that they satisfy this condition. Yes. Tau and delta are the variables here. Okay. So coming to your problem here, I think, is it this one? Where did I do that? Yes. Now can you tell me what is trace of J1? Trace of J1 is minus 2a x1 star, isn't it? This is J. Take the sum of two diagonal entities, minus 2a x1 star plus 0. What is determinant of J1? B minus B. Okay. What is trace of J2? Same, minus 2a x2 star, and determinant of J2 is minus B. Now, can you give me the condition on trace and determinant so that the value will be inside the triangle? See this example again. The best part of this is one entity you can easily tell without just looking it. Delta is less than 1 is one condition, isn't it? Delta always should be less than 1. Why? See, delta equals to 1 is this line, right? So here delta will be less than 1 in the green point, and here delta will be greater than 1. Why? Because this is the delta axis. This is the delta axis, isn't it? Is it okay with you? This is the delta axis. Therefore, if this line is delta equal to 1, this point should have delta less than 1, should have delta greater than 1. Okay, fine. So one condition you know is delta is less than 1. One condition is delta is less than 1. What is another condition? If delta is less than 1, your points will lie below this. You are safe. But your points should also lie in this region also, no? In these regions. It cannot go outside for it to be stable. So either like take these guys here on that side, you will get 1 plus delta plus 1 plus tau plus delta equal to 0, isn't it? Fine. Okay. Yes. Now on this side, since this is equal to, can we take one guy to prove this? I'll tell you, I'll just hear my words. You can easily feel this. This is 0, 0, isn't it? This is 0, 0. Substitute this value onto this. What you get? 1 plus 0 is greater than 0, isn't it? Yes. That means on this side, if your point has to lie on this side, it should have 1 plus tau plus delta greater than 0. Yes. Okay, with everyone with me? Mr. Abdul Bilal, is it okay? Can you tell me the similar condition for this line? Can you rewrite this line? 1 plus 1 minus tau plus delta equal to 0. I can rewrite this as. Okay, this is the line. I want to see, I want to check whether on this side, what is the sign of this quantity, 1 minus tau plus delta. So just take this example. It should satisfy for all points. So I am taking my best candidate and easy, that is 0, 0. That is my best candidate. I have to check only one point and see the condition. Put 0, 0 here, what you get? 1, that is greater than 0. So that means on this, if a point lies here, then it should satisfy 1 minus tau plus delta greater than 0. Okay, so you have one more condition here, 1 minus tau plus delta greater than 0. Okay, so now you can easily simplify this. So now what we derived, if your fixed point needs to be stable in a 2D map, then you compute the trace of the Jacobian matrix, compute the determinant of the Jacobian matrix, that is tau is the trace, determinant is delta. It should satisfy this guy. Delta should be less than 1. 1 plus tau plus delta should be greater than 0. 1 minus tau plus delta should be greater than 0. Okay. These three conditions, if it satisfies, then your tau delta points will be inside this invertible triangle, inside this inverted triangle. Okay, that's the condition. Okay, so let us come to our problem now. I think here I did, isn't it? Now, can you compute this? So from here, what we need, delta to be less than 1. Delta to be less than 1. Okay. So can you tell me? Let me remove these guys. They just came out of nowhere. Let us try again. Okay. Let us focus on this part very clearly. So for this guy, let us see what are the conditions. Delta should be less than 1. 1 plus tau plus delta should be greater than 0. 1 minus tau plus delta should be greater than 0, isn't it? What we learned so far. Okay with you? Now just tell me, delta less than 1 means, can you tell me here? Minus b is less than 1 or, oh no. This happens with me always. Minus b is less than 1. Can you tell me this value? 1 minus tau is 2a x1 star. Look here, the values. Delta is minus b. This should be greater than 0. From here, what you get? 1 plus 2a x1 star minus b greater than 0. Now you can see, now else you had to compute the eigenvalues, very complicated, and put those conditions less than 1, bit difficult. Instead, you derive these tiny 3 inequalities, simple 2 inequalities, which will give you the stability. So it's okay if you did not understand the derivation, how we got these conditions, but just remember this condition that after you find the fixed point, compute the trace and determinant of the Jacobian matrix, and then use these conditions. Determinant should be less than 1. 1 plus the trace plus delta. 1 plus tau plus delta should be greater than 0. 1 minus tau plus delta should be greater than 0. Okay, these are the 3 conditions. So try to do this with this also. So I gave you 2 different approaches. One, you can compute eigenvalue as usual and put mod of lambda 1 less than 1 and mod of lambda 2 to be less than 1 and solve for stability. That is step 1. Step 2 is geometrical, that is trace determinant plane. Just these three conditions. Okay. Okay with you? Hmm? First. Huh? Was it fast? Okay, speed. Speed is okay, no? So next class, maybe one of you can come to the board and do this. Okay. One of you should come to the board. There should be two people. One will solve for fixed point x1 star, y1 star. Another one will solve for x2 star, y2 star. Stability conditions. Okay. Here, the board will be divided into two parts. And one of them will do for x1 star, y1 star. Another will do for x2 star, y2 star. Okay. See, now why I am saying this is you saw this very nice looking images here. Okay. But hidden inside are the fixed points. So you should know how the stability is constructed, isn't it? Okay. Mr. Anand. Yeah, maybe it is too big because you are learning a lot of things in the same time. But when you do it, it is pretty okay. Just some calculations like root over squaring and all. But else, just need the concept. That's it. Nothing much. Fine. So, saying anything? Anyone saying anything? What is the issue? No. You go. Okay. So, we will see this some more properties of the map. Okay. So some more properties of the Henon map. More properties of Henon map. What happened? Okay. Okay, so can you tell me the Henon map? We had the Henon map as both these quantities xn plus 1, yn plus 1. Okay, so yeah, so what is the concept of a map? You have we are taking this 2D map. Okay, we are taking this 2D map x and y. What is our concept? You start from one point x naught y naught. Okay, that is the initial condition, isn't it? This is known as the initial condition. Yeah, so this is the initial condition. And what we do, we apply our map f. We apply the map f. You know, this point will go to some other point, isn't it? This point will go to some point. Maybe x1, y1. And what again happens? You again apply the map f. It goes to x2, y2. Okay. Apply the map f. Goes to x3, y3. Fine. Now, like there is a very important concept here, which might have crossed to your mind or might not have, but I want to illustrate that. The idea is we are always going forward. We are always going forward. Like from x naught, y naught, you apply f, you go forward x1, y1, apply f, x2, y2, and so on. Now, I want to ask a question that suppose I am here at x1, y1, okay? I want to go back. I want to go back. Like I want to know what points gave me the point x1, y1. What points you understood? Now, till now, we are going from x0, y0, x1, y1, x2, y2, and so on. Okay. Now I'm asking, we are at a point x1, y1. I am asking which points on this 2D plane. there can be 2 points. There can be A and B. Of course, x0, y0 is 1 point. A is another point. There can be 2 points which can map to x1, y1 under F. I have just shown x0, y0, but there can be more than one. Okay. Now, is it possible? That's what we are seeing in this phenomenon. Is it possible? What do you think? So what you can do, you have to take F inverse. Does F inverse exist? Does F inverse exist? What you do, if you do, so I'll write it here. X1, Y1 is equals to F of X0, Y0, isn't it? So you started from here, you applied F and you went to X1, Y1. Okay. So X1, Y1 is F of X0, comma Y. Yes. Now I'm asking which point map to x1, y1? What is the pre-image of x1, y1? That means you have to take inverse of x1, y1 and that will give you x0, y0. Okay. But x0, y0 is just one candidate. What are the other possible candidates we want to see? Okay. So that's what is my question to you. Okay. Can you let me know? Can you let me know if that is the case? Yes. So what you can do is, now I'm writing xn plus 1 equal to this guy in terms of, so how I'm writing xn plus 1 in terms of xn yn. I am writing yn plus 1 in terms of g of xn yn, isn't it? This is the map F, like, yes, this is the map F, capital F. Now I want F inverse. What is F inverse? So what you have to write? You have to write xn and yn in terms of like xn plus 1 and yn plus 1. Can you write it? That's my question. That's my question. Okay. What do you think? Let us take maybe this 2D example is a bit hard. Let us take this 1D example. Xn plus 1 is R xn into 1 minus xn, our famous logistic map. Okay. Here I want to ask you, can you write xn in terms of xn plus 1? Can you write xn in terms of xn plus 1? Yeah. Yes. Can you write xn in terms of xn plus 1? I think yes. Why can't you? Yeah, Rxn minus Rxn square is equal to xn plus 1. You can treat this as a quadratic equation. Yes. So Rxn squared minus Rxn plus xn plus 1 is equal to 0, isn't it? Can you write, give me xn, xn equal to minus b, that is R plus minus root over what you can say? B square is minus 4R xn plus 1 by 2R. Okay. So you got two xn points which map to one single xn, isn't it? What you can say? This is, there is xn1, xn2 such that f of xn1 maps to what? To xn plus 1. Also, there is another point xn2 which map to xn plus 1, isn't it? There are 2 points xn1 and xn2 which map to xn plus 1. That is our aim, isn't it? How many of you did not get this? Or how many of you got? Yeah. So there are 2 points which map to a single point. So therefore, what is your conclusion? Is this map invertible? No, there doesn't exist a unique inverse. Therefore, it is non-invertible. Okay. Due to this non-invertible nature, there is this stretching and folding action which you just saw. Okay, you saw, right? You saw this action here. You saw all this action here. Okay. This was only possible. Can a map do that? You don't have a control on the map. We are saying like, let it do this, like let it do a parabola, then do another one, stretch, stretch, stretch like this. But it is only possible if your map is non-invertible. That means it has more than one pre-image. Okay. So therefore, checking non-invertibility of the map is an important thing. Hmm? Maybe Miss Shweta can think like she's working on circle map, which is the topic of next class. You can think if circle map is invertible or not. Okay, fine. So yeah, this is the thing. You can actually characterize invertibility and non-invertibility of the map to see the chaotic property of the map. Okay. So if a map is invertible, if a map is non-invertible, it is responsible. It is responsible for the stretching and folding action. Stretching and folding action of the map. Okay. So that's what you saw in the Baker's map. The animation I just showed of the boomer example, the blue and the red part, they were mixing with each other. Okay. If you carefully look into this, the Baker map is also non-invertible. Okay, the Baker's map is also non-invertible. Okay. And due to that, it mixes nicely. Due to the non-invertibility property, it is mixing very nicely. Okay. So yeah. I think, do you have in your notes the Jacobian of the matrix of Henon map? Do you have the Jacobian of the Henon map with you? This is the Jacobian, right? This is the Jacobian, isn't it? Minus 2ax, 1, b0. Hmm? Let us consider this a bit more. Can you tell me that? J is minus 2ax. Huh. So this is the Jacobian map. Okay, this is the Jacobian map. Now, can you compute the determinant of this Jacobian? Minus b. Okay. Now, determinant has a very nice action on the 2D map. Determinant is responsible for the stretching and contraction, like contraction and expansion of the map. Okay. So determinant is, do you know that determinant has a relation with area? You can write determinant like determinant of a 2 by 2 matrix represents area of a, what is geometric interpretation of a determinant? Determinant implies area of the parallelogram. Okay, try to see that. Okay, what is the geometric interpretation of a determinant? So therefore I am going to do that. Okay, so if mod b is less than 1, then areas shrink. Okay, areas shrink under Henon map, under the Henon map. Okay, so if you set mod b is less than 1, then if you set mod b less than 1 and take an area, some area, bigger area, okay, and apply the Henon map, then the area will shrink. Okay, that's the property of this. So areas will shrink in this. If you have mod b less greater than 1, what will happen? Areas they expand. Which expand by b, by a factor of b. Huh? No, determinant is equal to b. Determinant is coming to be minus b. Right? If like b is greater than 1, the mod of b is greater than 1, then your areas expand. How much? Yes, it depends on the map. Depends, you have to check. But that I don't think you can measure it so nicely. It will not have a simple form because the map is itself non-linear. You are doing a non-linear area change. Okay, you are doing a non-linear area change. Okay, why I am so concerned about this? Why I always tell that, you remember that I always started from this, isn't it? Like you take a strip and apply the Henon map to it, and it will change this way. Okay, why I am so worried about areas? Can anyone tell? You can see this. These areas represent as image. Okay, image. I think mini project students, mini project, Mr. Akul Murali and Miss Sandra, they worked on image encryption. Okay, somewhat. Okay. So, so what they took the map, they took the image, and what the image is made of? Image is made up of the collection of pixels. Okay, and you can treat those pixels as the location of the XY points. Yes. Yes. And location of the XY points and apply the map, chaotic map. And it will disturb the pixel positions. Like that, you can encrypt an image. Okay. And you can use that chaotic map as a key to decrypt that image also. Okay. So therefore, these chaotic maps are useful in cybersecurity. In here, we don't require inverse. That yes, that's a good point. Yeah, in those cases, it would be good if you take a non-invertible map. Why it is good to have a non-invertible map? Suppose if you have a non-invertible map, if from one pixel you are going to the other pixel, and suppose someone got a hold of that map, that you are applying this to encrypt that image, then if it is just invertible, he can go back, apply the inverse and go to the original image and see what is the information, and your privacy is lost. Okay. So therefore, what will happen if you take a non-invertible map? Since you have shuffled a pixel, now your friend cannot reshuffle the pixel back to its original place. Why? Because while reshuffling back to the original place, he will apply the F inverse, but there will be more than one inverse. Okay, so it might not lead to the correct position. It might lead to the different position. So therefore, taking a non-invertible and extremely chaotic map is a good application for image encryption. I think Mr. Anandik and Halima, they are doing the mini project on video encryption using chaos. Soon they will show us the results. Okay. So they are using YOLO V5. Okay. So I think I'll just tell something about your project just now. So, yeah. So, yes. So what is happening is you must have seen very sensitive news on the news. Like someone is saying something, but their face is blurred. They don't want to reveal themselves, isn't it? Yeah. So that's the case. If they are revealed, then it is harm to them also. Hmm? So how they select that part of the image, but other part of the image is not blurred. They are done by that you can easily download and do that segmentation. That I want to blur this image, I want to detect this image and segment this image. Okay, and that face has to be blurred in all the frame of the video. Okay, if it is blurred in one frame and it is not blurred in another frame, then there is no use. Okay, yeah. So yes, so yeah. Therefore you can encrypt. I think. Yeah. So then after getting blurred, okay, after getting blurred, you can apply the chaotic map. I think I gave you the chaotic map, right? Yes. So you can take that chaotic map and apply the image encryption technique. Okay. Okay. Yeah. So this is what I wanted to talk. Okay. And what happens? I did not talk you about one more thing. What happens if you take B to be 1? Can you tell? What happens if you take B to be 1? Please, someone answer me. Like, yeah, just answer. Like, what is B equals to 1? What happens if B equals to 1? 1, then your folding might, okay, folding is not strong enough to produce chaos, to lead to chaos. Okay. What happens if what happens if B is close to 0? B is close to 0. Huh? No, actually. No, no. I suggest you can try some experiments with this. B is very small to 0. Try to plot the Henon map. You will see something known as a strong folding and squashing. Strong folding and squashing. Region. Mod B is less than 1. And I told you, but if B is very tiny, like close to 0, then it will be extreme high level of folding. High level of folding. I suggest those who are interested can play around with this in your Henon map. If the code you already wrote, right? So you can just change the value of B accordingly and see this. Maybe what you can do, maybe this can be a project also. Maybe this can be a project also. Take it. Your photo you can take. Maybe Jaydev's photo you can take. Okay. So suppose this is photo, Mr. Jaydev's photo. Okay. And you apply Henon map to it. Okay. You apply the chaotic Henon map. What it will do? Yeah. How Jaydev's image is getting transformed. Try to see. Okay. Whether can you recognize Jaydev after the chaos has been applied to Jaydev? Okay. When chaos is applied to Jaydev, whether Jaydev still exists? You have to see. Okay. Whether image of Jaydev still there. So please try, someone try to do this just as a fun. Okay. You can use your images to, yeah, this can be a good class project, isn't it? After 2 weeks, maybe I can see this. After 2 weeks, huh? You take Jaydev's image, anyone's image, apply the chaotic Henon map, and I want to see the output, how it looks. So this can be a fun project to begin with. So yeah, this is what I wanted to talk. One more thing, like I just wanted to say is, cannot be 0. That is a good question. That is a good question. Can B be 0? What do you think? What do you think? Can B be 0? Huh? Area? Yeah. B can be very close to 0, but B cannot be 0. Why? If B is equal to 0, can you see? We are converting to a 1D map. If B equal to 0, this 2D map is just converting to a 1D map. Just 1D map, nothing else. So I think you remember the map, isn't it? This was your logistic map, right? Now you can see that this is xn. This is xn plus 1. Okay. For any xn you take, there are two xn's which give the same xn plus 1 value. Just draw a line here. This xn and xn2 will give you the same xn plus 1 value. So therefore, this is another way of seeing that the logistic map is not invertible. Okay. Okay. Yeah. So these are two important concepts I have discussed in the last part of the class. These are important. Okay. Maybe it can be asked, what you think? Graphically show that the logistic map is not invertible. Graphically and analytically show that the logistic map is non-invertible. You have to draw this, show that these 2 points can map to xn plus 1, therefore it is non-invertible, and you can compute the root and show there are two pre-images also. Here I computed two pre-images. Can you see this? Two pre-images. And you are exactly getting those two pre-images here. For logistic map, it is debunked. For Henon map, you have to answer me. Question can come like this. For both question can come. For 1D and 2D. Maybe we can stop here. Stop here. And when should be our next class? Now only you tell.